Hey all, today we're going to have a conversation about the probability rules we started talking about in the last lesson, but we're going to get more specific. So we talked about the addition rule last time. If we have two disjoint events and we want to find the probability of one or the other thing happening, we can just add the probabilities together. But I said that there's different cases where they're not disjoint and that we'd have to adjust that rule. And so we're going to talk about that today. So take a second and read through this problem and question. So we have these students in a college, and some of them live on campus, some of them have a meal plan, and some of them have both. Just so you know, you don't always have to live on campus to have a meal plan, and you don't always have to have a meal plan if you live on campus. So we can create a Venn diagram to represent this scenario. And I'm going to let this circle be people who live on campus, L, and this circle be meal plan hat people, M. And this overlap is the people who have both. So these are not disjoint events. They can happen at the same time. So as a review, if I have 56% that live on campus, 42% of them also have a meal plan that goes in the middle, and the rest of them over here live on campus with no meal plan. 62% have a meal plan. The 42% that live on campus are in the middle, and the 20% that don't live on campus but still have a meal plan are over here. And then our probabilities always have to add up to 1, remember? So if I add these three across, I get 76. And so that means 24% of my students don't live on campus and don't have a meal plan. So that's like when I was a grad student, I lived in an apartment off campus and I bought my own groceries. So they're not disjoint events. So if we want to find this probability that a randomly selected student lives on campus or eats on campus, then I need to use a different formula. So we'll add those probabilities together still, but then we're going to have to take away this amount, the probability that they both happen at the same time, and that's at 42%. If we just add 56 and 62 together, we're counting these people in the middle twice, so we need to subtract that once. And what we end up with is 76% chance that we randomly select somebody who lives on campus or has a meal plan. So now we want to find the probability a randomly selected student lives off campus and doesn't have a meal plan. So we can use our Venn diagram again. We're going to do the complement of living on campus and the complement of having a meal plan. And those are those people in the box, not in the circle. That's our 24%. And the last question is we want the probability a randomly selected student lives on campus but doesn't have a meal plan. So in our Venn diagram, these people who are living on campus with no meal plan are over here. So that means that the probability we randomly select a student that is living on campus with no meal plan is 14%. So these Venn diagrams are actually really helpful in finding some of these probabilities. Now these second two probabilities were and probabilities. This formula up here goes with an or probability when we don't have disjoint events. And I know I'm going through these fast. I'm trying not to make this a super long video. Just trying to do the best we can here distance-wise. So we have these other probabilities called conditional probabilities. So we're going to use our same scenario of students living on campus and having meal plans. And so this time we're already in a dining facility eating with somebody that you've just met. Since they're in the dining facility, they definitely have a meal plan, so we already know something about them. And so we want to know the probability that that person that we just met, who is in a dining hall eating, also lives on campus. And so that's called a conditional probability. And so this probability statement reads, what is the probability of event B given, this line means given, event A has already happened. So in our scenario, we want to know the probability the student lives on campus given they have a meal plan. We already know they have a meal plan. And so we find that by taking the probability that they both happen, that and probability, and dividing by the probability that that student has a meal plan. And so if you notice in this formula, the thing that comes second, the thing that we're given, is what ends up on the bottom. And so we take our probabilities that we know, the 42% overlap goes on top, 62% of students have a meal plan, that whole circle, and we get approximately a 67.7% chance that that person we're eating with lives on campus. So along with that conditional probability, sometimes we want to know if events, we can use that to decide if events are independent. And then we also want to know if these are disjoint events. We already know that they're not disjoint. And it's important to note that two events can be one or the other, independent or disjoint, but they cannot be both. But they can be neither. So we can have two events that are not disjoint and not independent. Okay, so we know they're not disjoint. We've already talked about that. There's an overlap. There are some people who live on campus and have a meal plan, 42% of them to be exact. And so they're not disjoint events. So let's check in on the independence. If they're independent, then the probability of event B happening, given event A already happened, will be equal to event B happening even if A didn't happen. So that means that like event A didn't change the probability of event B happening. So that's a little abstract. So in relation to our problem, if the probability of somebody having a meal plan given that they live on campus is the same as the probability that they have a meal plan in general, then those events will be independent. If they're different, that means that the living on campus part affected the probability that you have a meal plan. So we can find the probability of having a meal plan given that they lived on campus using our formula. Probability they both happen is 42%. The probability of living on campus is 56%. So there's a 75% chance that somebody has a meal plan if we already know that they live on campus. And we know from the problem that the probability of anybody having a meal plan is 62%. Those two probabilities are not equal, and therefore they're not independent. That means that living on campus changes the probability that you have a meal plan. And that probably makes sense. More people who live on campus are going to eat on campus as well. We also talked about the multiplication rule. This applies to events that are independent or not independent. And if we want to find an and probability, the probability that both things happen, if they're independent, we can just multiply the two probabilities together. If not, we have to do something different. So go ahead and read this about batteries. So we have this company that makes batteries, some regular and some rechargeable. And then of course, some of them are defective. And so we want to know the probability that if we randomly pick a battery off the line, that we get a defective rechargeable battery. So that's like saying we get a battery that is defective and rechargeable. So since the defective batteries in each category are different, that means that these are not independent events. The battery being rechargeable or regular is going to change the probability of it being defective. And so we need to use a different rule. When they're not independent, we take the probability of event A happening, and then we multiply it by the probability of event B happening given A already happened. So we're going to find the probability that we have a rechargeable battery and it's defective. So we find the probability that it's rechargeable, and then the probability that it's defective given it's rechargeable. So we have those values. 25% of them are rechargeable, and 1% of those rechargeable batteries are defective. So approximately 0.25% of them will be, I'm sorry, we have a 0.25% chance, so less than 1% chance that we randomly select a rechargeable defective battery. So now we're choosing one at random, and we want to know the probability that it's a regular battery and it's not defective. So we're going to find the probability it's a regular battery, which is 75%, and then the probability that it's not defective or working given it's a regular battery. So 98% of those regular batteries work. And so we have a 73.5% chance of pulling a battery off the line that is a regular battery that works. So another way to sort of get events where one event will change the probability of another one is when we have this thing called drawing without replacement. So that's like we take something out of the sample space and don't replace it. The easiest example is a deck of cards. We draw a card out of a deck and we don't put it back. In this example, we're going to be talking about Skittles and taking a Skittles candy out of the bag and not replacing it. Therefore, we'll change the probability of getting a different Skittles. Take a second and read this. These are in the book, by the way, as well, if you want to take a look at how they did them. So we have these 20 Skittles in a bag of Skittles, and they're all different colors. We don't know how many are in there. And so we want to find the probability that if we take one Skittle out at a time, our first two Skittles are orange. So we have 5 of the 20 candies that are orange. So the first time we draw one of the candies out, we have a 5 out of 20 chance of getting an orange candy. But once that orange candy is gone, we've eaten it, it's not in the bag, there's one less candy and there's one less orange candy. And so therefore the probability of an orange candy coming up next is going to change. So we have an AND probability. They're not independent events, so we have to take the probability of the first thing happening and multiply it by the conditional probability of the second event happening. So probability of my first orange was 5 out of 20. My second orange, there's only 4 oranges left because I already picked one. There's only 19 candies left because I already picked one. And so the probability of an orange now is 4 out of 19. And so when we multiply that and simplify, we have a 1 in 19 chance of picking 2 oranges on the first 2 Skittles. So now we want to know the probability that none of our first 3 are green. So said another way, we want to know that the probability of selecting 3 candies that are not green on the first try. So that's the probability of not getting green and not getting green and not getting green. So there's 13 candies to start with that are not green out of 20. And then if we pick a not green one out, there's 12 left over that aren't green out of 19. And then we pick another green out, there's 11 non-greens divided by 18 candies left. And when we do that multiplication, we get about 25%. So there's about a 25% chance of selecting 3 candies in a row that are not green. Hopefully if you hung with me, this is our last page. I know this is a little long, it's a little fast. Make sure that you ask me any and all questions that you might have, especially when you're working through practice. We can create tree diagrams to try and model scenarios so that we can find probabilities easier. It's not something you have to do, but it can be helpful. So we're going to go back to our rechargeable and regular battery scenario. So same numbers and values. And so what we want to know is that if we randomly choose a battery from a shipment from this factory, we want to know if that battery will be defective. So we don't care if it's rechargeable or regular, we just want to know the probability it's defective. So we can set up what's called a tree diagram. We have a shipment of batteries. 75% of them are regular batteries, 25% of them are rechargeable. And then of those regular batteries, 2% are defective, 98% are not defective. The rechargeables, 1% are defective, 99% are not defective. And so we can find all these probabilities, the probability of being regular and defective, regular and not defective, rechargeable, defective, rechargeable, not defective, just by multiplying using the multiplication rule. So 0.75 times 0.2, 0.75 times 0.8, 0.25 times 0.01, 0.25 times 0.99. And so those are the 4 scenarios. If you add all 4 of these up, you should get 1, because these are the only 4 options here. And so when we want to find the probability of getting a defective battery, what do we want? We want it to be rechargeable given it's defective. I'm sorry, I didn't maybe ask the question correctly. So we have both rechargeable and regular batteries that are defective. So if I pick this battery up and I know it doesn't work, we want to know the probability that it's rechargeable. So that's a conditional probability. We find the probability that it's rechargeable and it's defective, that 0.025 right there. And then we have to divide that by the probability it's defective. So we have to take these 2 probabilities, my regular batteries that are defective and my rechargeable batteries are defective, and add them together. They're disjoint events because they can't be both regular and rechargeable and defective at the same time, so we can just add those together and we get a probability of 0.143. We went fast. We're not together to do this. If it's confusing, it's okay. Make sure that you send me messages, send me emails, send me pictures of your questions. Any help that you need, let me know. I'm available today, Tuesday from 1 to 3, and Thursday from 8 to 9. Outside of those hours, I'm available as well. Just send me an email, and I'll try to respond to you in a reasonable amount of time.